Hello, and welcome back to another video where we explore the boundaries of space and time and for loops. That is, we launch rockets through time and space using Kerbal Operating System in KSP. And quickly before we jump in, I want to say how much I appreciate your patience with this series. As some of you know, we're moving into our first home, and of course moving out of our apartment, which is eating up a lot of time, but also means that my equipment is spread across 2 different places. My recording booth and my gaming PC, for example, are across town from one another, so I appreciate you being patient with the upload schedule, and I appreciate your patience in advance for a bit of the audio quality. Up until now, I've been doing my best to avoid leaning too much into the math of things, and the reason for that is that a lot of people have had a bad experience with math in school, and it can tend to scare people away. But I think that it's a little different when you actually care about the answer. We can think of our autopilot script as one of those math story problems, except if we get the answer wrong, our ship explodes. So that's a little incentive right there. In fact, I've already slipped a little bit of math past you in previous videos. Well, slipped it past most of you, I should say. We're using a fancy mathematical equation in our ascent script, and it's probably worth backing up a step to look at where that came from. I've seen, and written, a lot of newbie launch scripts in kOS, and a lot of times you'll wind up with something like this. You'll have the initial setup, then a series of wait until commands. This is the author's way of shepherding the craft to orbit by slowly tipping the rocket over. At first, we lock the steering to a heading of 90 degrees, which means east, and 90 degrees off the horizon. When we reach 10 kilometers up, then we steer to 90 degrees in the compass direction still, but 80 degrees off the horizon. We're beginning a gravity turn. Once we hit 15 kilometers, we'll adjust to 70 degrees off the horizon. And of course, this makes sense. As our altitude gets higher, we want to tip our rocket further and further over. This is one way to do that. But there are some real issues with this sort of approach. For one, the script has to wait at each of these points, which can make staging a bit of a challenge, though there are some fixes for that. And technically speaking, we really shouldn't care about our altitude when we're deciding how much energy to spend fighting gravity versus giving us sideways momentum. We should care about our apoapsis. Though we could rewrite all of these weight conditions to be based off of that as well. But the biggest issue is that the rocket really should be smoothly adjusting between these set points. Instead, we wait as our altitude increases, then tip over all of a sudden. Wait a little more, suddenly tip over a little more. This is going to be choppy and it's hard to tweak. We'd need to run hundreds of launches to tweak each of these points to be just right. But if we stop and think about what we're doing, you might notice that we're not actually just describing a sequence of events. We're actually trying to describe a relationship between our altitude, or apoapsis, and our angle off of the horizon. That is, like it or not, a mathematical function. So let's go through how we would turn this series of steps into a function. Presumably we're going to end up with something. This 90 is constant, but these values change. So we'll end up with something along the lines of lock steering to heading 90, and then some formula, right? Something to do with our alt radar times something, etc. I don't know what it's going to be. But rather than actually solve this ourselves, what I want to show you is that we can actually just get Wolfram Alpha to do this for us. So we know that initially we want at zero, altitude of 0, we want to be 90 degrees off the horizon. At an altitude of 10,000, we want to be 80 degrees off the horizon. And 1500, 70 degrees. So let's jump over to Wolfram Alpha, and I'll show you how we can make it derive our function for us. So here I am on Wolfram Alpha, which is kind of the, free math for all. And I'm going to say fit, and I'm going to give it these parentheses. And inside these parentheses, I'm going to put these pairs of values. So we know that we have a 0, and that gives us 90 degrees off the horizon. I'll put a comma there. And then at, 10,000, we want it to be 80 degrees. And at 15, then it was 70 degrees. And the values don't actually matter too much here, because I'm just showing this as an example. So if I'm wrong here, that's fine. And so I've told it, hey, fit this set of data. And I'm just going to hit enter. And it says, okay, it's computing. And it says, hey, least squares best fit diagnostics, blah, 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 blah. And it gives us this lovely little graph, which is not particularly helpful, because it is trying a periodic fit, which is your cosine. It's going to go up and down a lot. It shows us, here's our data. Let's tell it to do a quadratic fit. And if we let it try that time, now it's just going to do that type of fit, because it tries a bunch of different strategies. And we can see, hey, look, now it gives us this wonderful way to say, hey, given any particular altitude, this is what our angle off the horizon should be. Instead of using this data, we can use this formula. So if I were to copy this, let's get this in plain text. Then we know that our input is the alt radar. So I'm just going to copy this in here. Instead, we're just going to say angle. And then we'll say lock angle to, and it's going to be blah, bitty, blah, bitty, blah. And we can convert this to kOS code. We're going to put a dot there. All of these X's are our alt radars, because that's the input variable. And we can do the same thing here, alt radar. And this times that, so we can actually just do E, I think. Pretty sure that's valid. If not, you may need to go ahead and look at the docs and double check that. But what we said is, hey, lock this angle to this formula. And of course, it has sort of implicit multiplications. We've got to do that. So -4 times 5, blah, 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 times alt radar, blah. In fact, if we jump back over, we can probably just do a linear fit that's going to get us pretty darn close. But this is just giving us the happy little formula that will take our angle from 90 degrees down to 0, fitting that curve so that it matches all of this logic, which means that we can go ahead and now just remove all of these weights and just represent the relationship between the angle off the horizon and our altitude as a simple function. So way back over here in our original script where we have this do ascent function, I've done exactly that. I have lock target pitch to, and this is the formula that I happen to come up with that worked for me using the data that I pulled in. In fact, it's not even something that I pulled in. This is one that we let a genetic algorithm derive in a video from a series way back. If you want to go ahead and take a look at that, I'll have a link up on the screen. But this is exactly what we're doing. We're saying, hey, the target pitch is 88.963 minus some factor that increases over time. So we go from 88.9 degrees off the horizon down to 0 over time, and we set the target direction to 90, and then we just lock the steering to that heading. So that's been sort of sneakily hiding out in here instead of a bunch of sequences of steps, because it makes things really clean. We don't have to wait till we get to these particular breakpoints and then tip over more, so we can handle staging and not worry about making sure the pitch is on target. So this works, and we've snuck in a little bit of math. Now let's do so a little bit more deliberately. So today we need to get back to filling out this maneuver burn time function that's supposed to calculate how long it takes us to execute a maneuver. And I've taken the liberty of commenting out a lot of our main script and just setting up a little way for us to quickly test whether or not things are working. I've said set RCS to off, and then until false, wait until RCS. We're just going to wait until RCS is turned on, and then it's going to print the maneuver burn time of whatever the next node in our flight path is, and then it's going to turn RCS off again. So this is a way that we can just quickly take our craft in orbit, try out this maneuver burn time function, have it print out the value that it gets, and then do that over and over and over. So we can throw a maneuver node on the path. We can see, hey, okay, this is what the estimate actually is. We can hit RCS and then tell it have it print out what it thinks that time is going to be. So, okay. Maneuver burn time. We need to figure out, we have a maneuver node, and that maneuver node has a certain amount of delta V, and we're trying to figure out how long is it going to take our craft to execute that. So how do we even begin? We begin with the Tsiolkovsky Rocket Equation, or the ideal rocket equation. And this is Wikipedia. I've just got an extension called WikiWan that makes it look a little bit nicer and more readable. So this gives us some information about rockets. This is ways for us to calculate delta V. Now in this case, we actually know the delta V because that's what our maneuver is. It's a desired amount of change in velocity. So V is delta V, M0 is the initial total mass, including propellant, MF is the final total mass without propellant, and VE is the effective exhaust velocity. So we have this formula here. And it also says down here, this equation can also be written using the specific impulse instead of the effective exhaust velocity by applying the formula. The exhaust velocity equals the ISP, the specific impulse, times G0, where G0 is standard gravity. So the Tsiolkovsky Rocket Equation is as follows. dV, delta V, is equal to the velocity exhaust, velocity exhaust, something like that, I don't know, times the natural log of the M0 divided by the MF. So the initial mass divided by the final mass. Now, is this helpful at all? Not really, because what we're looking for is the maneuver burn time, right? We don't care about the velocity of the exhaust. We don't care about the final mass. We don't even care about the delta V because we already know it. It's part of what we're asking about. How do we get time from this? Well, I want to propose a formula to you that I'm not going to actually take from anywhere, but we can just sort of think about it and realize that it's true. We can say the initial mass, or well, the final mass, mf, is going to equal the initial mass minus the fuel flow rate times time. We use T for time. Right, that makes sense. So the final mass is whatever our starting mass is, minus however much fuel we spend a second times however many seconds we spent spending fuel, right? That makes intuitive sense. And I'm sure we could actually find this somewhere as well. So this actually looks like a way for us to plug in some stuff and maybe represent something in terms of T. That's pretty cool. Now, there's one final formula that we are going to need because this fuel flow value is one that we don't know. We don't know where to get that from. So let's jump back over to Wikipedia and steal some more math. And actually, before we do that, I do want to rewrite our equation here using specific impulse because that is something that we do get from our engines. It's information that we can query in kOS. It's information that you can see in the VAB when you're looking at the rockets. So let's rewrite that formula real quick and swap out the VE. And so instead, we can just go ahead and plug this in, times G0, and there we go. Now, I'm actually going to click into specific impulse because there is a formula that I happen to know is here that I think is useful. And it has to do, down here, specific impulse in seconds. And it's the general definition of what the specific impulse is. And we get this formula that the thrust is equal to G0 times the specific impulse times this mass flow rate. This is the fuel flow rate that we actually wanted. So we can go ahead and steal this formula too. F equals ISP times G0 times fuel flow. And of course, they used M, but whatever. We'll go ahead and use fuel flow because it's less confusing to me. And when we're doing programming, we don't have to use tiny little non-intuitive letters for things. We can use nice little helpful names. So that's great. So, okay, let's think about how we can start solving this. Do we have all of the information that we need? Well, the ISP is stuff that we can get from the engine. So yes, G0 is a constant. That's going to be 9.8. In fact, we can just set that. Local G0 is that. That's G0 from now into eternity. Hooray. The fuel flow, we're actually going to rewrite. We're going to get it from the thrust of our engines and the ISP and G0. I think we have all of the data that we need. So now we just need to start rewriting all of these formulas into the terms that we actually want. So let's start with this one because it actually has the term that we want, which is T. So we'll take this one. I'm just going to copy this formula and we'll go ahead and just algebraically start rewriting stuff. So let's see, MF plus fuel flow times T equals M0. So fuel flow times T equals M0 minus MF. So T equals fuel flow, M0 minus MF divided by fuel flow. Hurrah! So we have a formula that actually works. That's good for us. I'm going to put a dot after that to make it KSP-like. And we're going to say local T. And instead of using equals, we're actually doing assignment, so we have to say is. So cool. Now, of course, this implies that we have these values from somewhere, so we're going to need to rewrite these other formulas. This one we're done with, so we can even get rid of that. That's fine. And now, let's see what should we tackle next. Let's tackle this fuel flow value. So we need something that's going to give us fuel flow. We just need to rewrite this formula in terms of fuel flow. And that one should be pretty easy. So fuel flow, you just need to divide both sides by ISP times G0. So fuel flow equals ISP times G0 divided by F, which is our thrust. Well, F is fine. And of course, if we rewrite this, local fuel flow is ISP times G0 times divided by F. Now, some of these values we don't have assigned. We know we can get them, but we haven't written them just yet. We'll come back to that. So like F, we need to figure out. ISP, we're going to need to actually rewrite. G0, we do have assigned up here, so that one's great. M0 even, we don't have anywhere, though presumably we can get it. Now we need to rewrite the hard one. And what do we actually need from this? Well, we're trying to make sure that we can solve for these values. So we have M0. In fact, that's just ship mass. That's our initial mass. So we can go ahead and just use that. MF is what we're trying to solve. Local fuel flow we're defining up here. In fact, let's go ahead and rewrite all this. Ship max thrust is going to be, I'm going to capitalize that for fun. ISP we're going to save for a second. We'll just put that up there. In fact, I'll put that up there with G0, because that's more of a constant rather than a relationship. Okay, so now that means that the missing value that we have down here is MF. So we need to rewrite this whole thing in terms of MF, which is going to be a little bit messy. So let's go ahead and get started with that. Let's see. We divide both sides by ISP times G0. That equals the natural log M0 divided by MF. And of course, now we have to raise both sides. We need to raise E to both sides of the equation, which is messy. We'll go dV divided by ISP times G0. And that's going to equal M0 times MF, because E to the natural log of something is just the thing. Okay, multiply both sides by MF. Say MF times, and this is messy, and I understand why we might kind of shy away from some of this, and that's understandable. And then we'll just divide both sides by this ugly thing. So MF equals M0 divided by blah. Blech. This is gross. But we now have something in terms of MF. So that's great. Let's write that. Local MF is M0, which we know is ship mass. And E, we actually need to get it. There's a constants. Wow. Constant E. And then we can raise that to the power of dV divided by SP divided by G0. Now, actually, dV we don't have from anywhere, so we're going to need to grab that out of our maneuver. So we're going to say local dV is the maneuver, and this is, again, we need to look at the docs if we're not familiar with where this is at. So I'm going to get delta V magnitude. I'm going to get the magnitude of the delta V vector, because that's the total amount of change in velocity that we need. Okay, so in theory, we could combine these three functions and just plug in this right-hand side into here and plug in this right-hand side into here, but that seems ugly, and there's no reason for us to have to do that. So we'll go ahead and leave this alone. There's one last thing that we're missing, and it is the ISP. And I have realized in the course of double-checking my work against the stuff that I've actually tested that I had this backwards. Somehow I managed to get this flipped. The fuel flow is the ship max thrust divided by the ISP times G0. At some point, I screwed up my algebra. I'm sure you guys were cringing in the comments, but thankfully we've managed to fix that up. So now it's time for us to solve this ISP thing, and we want to make sure that this maneuver burn time function is robust, that it can work in a variety of circumstances. In our case, we can get the specific impulse for a particular engine, and we're only firing one engine at a time. But in other scripts, we may want to run multiple engines, and they may have different specific impulses. So what we actually have to do is we have to get a weighted average of the specific impulse. If one engine is the big engine and it has twice as much thrust as anything else, then its specific impulse is going to be the more relevant factor. So the first thing we need to do is actually get a list of all of the engines. And in the last video, we talked about all of the different ways there were to declare variables. Well, there's one more, and I forgot about it. And it's this: list engines in myEngines. I am implicitly creating this myEngines variable, and to be honest, I don't know if it's local or global. So if you want to go ahead and check, feel free to go ahead and do that, but we'll go ahead and just leave that alone. This is going to list all of the engines on our vessel into this variable. Now what we can do is we can loop over all of those. So we're going to go for en, for engine, and we'll do that in myEngines. And we're going to do something for every engine. We're going to check, first off, if this engine happens to be active, because we have some that are on stages that haven't been activated yet. So I'm going to say if en ignition and not en flameout. And this will generally get us all of the engines that are currently available to provide thrust. These are the ones that are contributing to this maneuver, and they're the ones that we need to total up their ISP. So the amount that their specific impulse is weighted is based on the amount of thrust that they provide. So what we're going to do is we're going to add their particular contribution to the specific impulse based on that weight. So I'm going to say set ISP to ISP plus, and now we have to do that thing. So we can get the ISP of just the engine, and that's great. But now we need to weight it by how much that engine is a factor. And that's engine max thrust divided by, and we'll put a parenthesis around there just to make it a little clearer, divided by ship max thrust. So if this is a rocket that an engine that has a tiny amount of thrust, and if we're shooting forward with a ton of thrust, well, then the ISP of that engine doesn't matter very much. But in our case, it's going to be 1-to-1. The engine's max thrust is going to be some number, and the ship's max thrust is going to be the same number because we only have one engine running at a time. So that's great. Okay, so now we've actually computed the ISP for our craft, the total amount of all of the engines that happen to be active at any point in time. So now we have this function. We have this math that's gone down here and been rather scary. We finally have that t value. Let's go ahead and return it, and we can jump over into KSP and start debugging all of the mistakes that I'm not yet sure that I've made yet. What? Grammar. All right, and here we are, and I've actually installed Kerbal Engineer Redux just because it's a little helpful in terms of determining our actual maneuver node burn times because, well, this one isn't so accurate. Its estimated burn is not available here because we haven't fired the engine since we loaded up this save, and this maneuver time calculator is not particularly accurate. It's based on how much you happen to be thrusting. We're assuming that we're going to be at full throttle. So we need to create a maneuver that is less than 669 so that we can actually compare what Kerbal Engineer thinks our maneuver time is going to be. So it thinks our node burn time is 13.7 seconds. We have this set up now on a loop waiting for us to hit RCS. And then once we do, it should print out what it thinks the value is. So let's see. How about that? 13.74. That is fantastic. Let's go ahead and adjust our maneuver a bit. All right, so that's total delta V of 297. It thinks it's going to take us 7 seconds. Let's see what we come up with. Oops. 7.03 seconds. There we go. Do another one. 11.2 seconds, 11.17 seconds. All right, you know what? I think we actually managed to load something up that happens to work on the first try. So that's fantastic. One last trick that I do want to show you is to do with Wolfram Alpha, because I understand that the math can be intimidating, especially if we've been kind of out of the math game for a while. Let's assume that we have some random function. Let's say, I don't know, well, let's take that ISP equals, what was it, G0? No, it was F equals G0 times ISP times fuel flow, just as an example. And let's say we just, for whatever reason, do not remember how to do things, or let's make it more complicated. Let's say it's fuel flow squared, and that's not accurate, but whatever it may happen to be. And we want to go ahead and rewrite this in terms of fuel flow. We want to solve this for fuel flow, and you don't remember quite how to do that? Well, that's okay. If you're uncomfortable with the algebra, we can jump over to Wolfram Alpha and just have it do it for us. First thing we're going to do is we're going to write ourselves a little key, because Wolfram Alpha doesn't like these long words. We have to write it in a more mathy way. So I'm going to say ISP is equal. We'll say ISP points is X and fuel flow is Y. And then we'll just go ahead and rewrite this formula, but plug in those values. So we'll say X and Y. And then we'll just say, hey, Wolfram Alpha, solve this for Y. Right, so I'm just going to paste in this equation, and it'll say, comma, solve for Y. Well, okay, so that's a little messy, but it does at least give it for us. If we had the simpler version, then I think it's going to give us a nice value. Yeah, so then we just get it. It just tells us, hey, Y is going to equal F over G0 times X. And then so we don't have to necessarily work through all of the algebra on our own. We can go ahead and cheat and hop over here if it happens to be helpful. So I hope that's not too intimidating. We're going to get back into more of the structure and looking at some of the functions so that we can get our way out to the moon, because that's what we've got to do next. I hope to see you then. Cheers.